Welcome! In this session, we'll explore an interesting coding problem titled Fruit into Baskets. This problem challenges us to maximize the number of fruits we can collect under specific constraints. Stay tuned as we break it down step by step and explore various approaches to solve it effectively. In this problem, you are tasked with collecting fruits from a row of trees, where each tree produces a specific type of fruit. These trees are represented as an integer array called fruits, and each number in the array corresponds to a type of fruit. The catch is that you are only allowed to use 2 baskets, and each basket can only hold one type of fruit. Your goal is to figure out the maximum number of fruits you can collect in total, but there's a limitation: the fruits you collect must come from a contiguous subarray of the fruits array. This means you can only pick fruits from consecutive trees. The final output should be the maximum number of fruits you can collect under these conditions. Let's look at an example to understand this better. If the input is fruits equals 1, 2, 1, the maximum number of fruits you can collect is 3. This is because you can pick fruits from all 3 trees, as they only contain 2 types of fruits, 1 and 2. Since the entire array forms a valid subarray with just 2 types of fruits, the result is 3. Now consider another example with fruits equals 0, 1, 2, 2. Here, the maximum number of fruits is also 3, but this time, the valid subarray is 1, 2, 2. Even though the array starts with 0, 1, it's not the longest subarray with only 2 types of fruits, so the output remains 3. For further clarity, let's analyze another example. Suppose the input is fruits equals 1, 2, 3, 2, 2. The maximum number of fruits you can collect is 4, and the valid subarray is 2, 3, 2, 2. This subarray contains exactly 2 types of fruits, 2 and 3, and it is the longest subarray that satisfies the condition. While other subarrays like 1, 2, or 3, 2, 2 also contain 2 types of fruits, their lengths are smaller than 4. Hence, the result in this case is 4. Now let's consider a more complex example. If the input is fruits equals 3, 3, 3, 1, 2, 1, 1, 2, 3, 3, 4, the maximum number of fruits you can collect is 5. The longest valid subarray here is 1, 2, 1, 1, 2, which contains 2 types of fruits, 1 and 2. While there are other subarrays with 2 types of fruits, like 3, 3, 3, or 2, 3, 3, their lengths are shorter compared to 1, 2, 1, 1, 2. Therefore, the output for this input is 5. It's important to note that the problem has constraints, such as the array's length being up to 10⁻⁵, and all values in the array being non-negative integers less than the array's length. Finally, let's highlight some key edge cases and efficiency requirements. If the fruits array contains only one type of fruit, the answer will simply be the length of the array, as only one basket is needed. If there are exactly 2 types of fruits in the array, the entire array is valid, and the result will again be the array's length. However, for large inputs where the length of fruits is up to 10⁻⁵, the solution must work efficiently in O(n) time complexity. This ensures that the problem can handle large datasets without performance issues. To solve the problem of finding the largest subarray containing at most 2 distinct fruit types, one approach we can consider is the brute force method. The idea here is straightforward: iterate through all possible subarrays of the input array and check each one to see if it meets the condition of having 2 or fewer distinct fruit types. If it does, we calculate its size and keep track of the largest valid subarray we find. Now, to implement this, we start by iterating over all possible starting indices of subarrays. For each starting index, we iterate over all possible ending indices, forming all subarrays between those points. Then, for each subarray, we check if it contains at most 2 distinct fruit types. If it does, we calculate its size and compare it with our maximum size so far, updating the maximum if needed. However, this approach has a time complexity of O(n) squared, because of the nested iterations, and it also uses O(n) space to store the distinct fruit types within each subarray. While the brute force method is simple to understand and easy to implement, it becomes computationally expensive as the input size grows, making it impractical for larger arrays where n can go up to 10,000. A more efficient solution is to use the sliding window approach, which is optimized to handle the constraints of this problem. The key observation here is that we are limited to at most 2 distinct fruit types in the subarray, which makes this problem similar to the longest subarray with k distinct elements, where k equals 2. Instead of checking all possible subarrays, we maintain a window that dynamically adjusts to contain at most 2 distinct fruit types. We use 2 pointers to represent the boundaries of this window and a hash map to track the count of each fruit type within the window. Starting with both pointers at the beginning, we expand the window by moving the end pointer and updating the hash map to include the new fruit. If the number of distinct fruit types inside the window exceeds 2, we shrink the window by moving the start pointer forward and updating the hash map to remove or adjust the count of fruits until the condition is met again. Throughout this process, we keep track of the maximum window size. This sliding window technique ensures that we only traverse the array once, giving us a time complexity of O(n), as each element is processed at most twice, and uses constant space for the hash map, as it only ever contains up to 2 distinct keys. Although the sliding window approach is more complex to implement than the brute force method, it is significantly more efficient and well suited for large inputs. This makes it the optimal choice for this problem. While the brute force method is simple, its O(n) squared time complexity renders it impractical for larger arrays with n up to 10,000. The sliding window approach, on the other hand, with its linear O(n) time complexity, scales seamlessly to larger inputs. The breakthrough in this problem lies in recognizing that we only need to track 2 distinct fruit types at any given time, which aligns perfectly with the sliding window paradigm. By dynamically adjusting the window size, we eliminate unnecessary computations and focus only on the relevant portions of the array. Overall, the sliding window technique strikes an excellent balance between efficiency and clarity, making it the preferred solution for this problem. It not only meets the performance requirements but also provides an elegant and intuitive way to solve the challenge. The problem at hand is to determine the length of the longest subarray of fruits that contains at most 2 distinct types of fruits. This is commonly referred to as the sliding window problem or the longest subarray with at most 2 distinct elements problem. Let's first explore a brute force approach to solve this. We start by generating all possible subarrays of the input array. For each starting index I, we iterate through all ending indices j to form subarrays. For example, if the input is 1, 2, 1, 3, we generate subarrays such as 1, 1, 2, 1, 2, 1, and so on. Then, for each subarray, we determine the number of distinct elements by converting the subarray into a set. Using this, we can see, for instance, that the subarray 1, 2, 1 has distinct elements 1, 2. If the number of distinct elements is less than or equal to 2, we calculate the size of the subarray, which is ji plus 1, and keep track of the maximum size found. For example, the size of 1, 2, 1 is 3. This process is repeated for all possible subarrays to find the largest valid one. Once all subarrays have been evaluated, the maximum size of all valid subarrays is returned as the result. However, the brute force approach has a significant drawback. Its time complexity is O(n) superscript 3, due to the nested loops and the repeated computation of distinct elements using a set. To optimize this, we use the sliding window approach, which reduces the time complexity to O(n). Here's how it works. First, we initialize 2 pointers, start and end, to define the sliding window, and use a dictionary to track the count of each fruit type within the window. For instance, with an input of 1, 2, 1, 3, we start with start equals 0, end equals 0, and an empty dictionary. Next, we expand the window by incrementing the end pointer. Each time we add the fruit at end to the dictionary and update its count. For example, adding the fruit 1 results in the dictionary 1, 1. If, at any point, the dictionary contains more than 2 distinct keys, we shrink the window by incrementing the start pointer. This involves decrementing the count of the fruit at start in the dictionary, and if its count reaches 0, the fruit is removed from the dictionary. For instance, if the dictionary has 1, 1, 2, 1, 3, 1, we increment start and adjust the dictionary until it contains at most 2 distinct fruit types again. As we dynamically adjust the window, we calculate its size as end start plus 1 and update the maximum size if the current window is larger than the previous maximum. For example, if start equals 0 and end equals 2, the size of the window is 3. Once the end pointer reaches the end of the array, the maximum size of all valid subarrays found during this process is returned as the final result. To understand why the sliding window approach is more efficient, consider that it avoids recalculating the distinct elements for overlapping subarrays by maintaining a dynamic window. This eliminates redundancy and ensures that the operations are performed incrementally. The dictionary plays a critical role here by efficiently tracking the counts of fruit types in constant time. This makes it possible to expand and shrink the window while keeping the operations fast and manageable. When implementing this approach, there are a few edge cases to consider. If the input array is empty, we simply return 0. If the array contains only one element, the longest subarray is the single element itself, so the result is 1. If all elements in the array are identical, the entire array is the longest valid subarray, and its length is returned. Finally, there is no scenario where no valid subarray exists, as any single element qualifies as a subarray with at most 2 distinct fruits. The sliding window itself is represented by the 2 pointers, start and end, which dynamically define the current subarray. The dictionary efficiently tracks the count of each fruit type in constant time, ensuring that the logic remains efficient. This leads to a time complexity of O(n), as each fruit is added and removed from the dictionary at most once, resulting in a single linear scan through the array. The space complexity is O(1), because the dictionary only ever stores at most 2 keys, regardless of the input size. Let's walk through an example to see the sliding window approach in action. Suppose the input is fruits equals 1, 2, 1, 3, 4. We start with start equals 0, end equals 0, and an empty dictionary. First, we expand the window by including the fruit at end, which is 1, updating the dictionary to 1, 1. Next, we include 2, making the dictionary 1, 1, 2, 1. Then, we include another 1, resulting in 1, 2, 2, 1. At this point, the window is valid, so we calculate its size. When we expand further to include 3, the dictionary becomes 1, 2, 2, 1, 3, 1, which violates the condition of having at most 2 distinct fruits. To restore the condition, we increment start and adjust the dictionary, eventually reaching 2, 1, 3, 1, with a valid window 2, 1, 3. This process continues until the end pointer reaches the end of the array, and the largest valid subarray size is determined. In this example, the result is 3. This Python implementation solves LeetCode problem number 904, fruit into baskets, using the sliding window technique. The goal of the problem is to find the longest subarray of fruits that contains at most 2 distinct types. Explanation *. 1. We initialize 2 pointers, left and right, to represent the current window of fruits being considered. Left starts at the beginning of the array, and right iterates throughout. 2. The basket dictionary acts as a count of each fruit type in the current window. Its keys are the fruit types, and values are their counts. 3. As the right pointer moves across the fruits array, the current fruit is added to the basket by increasing its count. If the basket contains more than 2 types of fruits, we shrink the window by incrementing left until the basket contains only 2 types again. For each increment of left, we decrease the count of the fruited fruits, left, and if its count drops to 0, we remove it from the basket. After ensuring the basket contains at most 2 types, we calculate the window size, right left plus 1, and update max_fruits with the maximum size encountered. 5. Finally, the function returns max_fruits, which is the length of the longest valid subarray. This approach is efficient, with a time complexity of O(n), where n is the length of the fruits array, because each element is processed at most twice, once by right and once by left. The space complexity is O(1), as the basket dictionary holds at most 2 keys at any time. This is the Java implementation of the fruit into baskets problem, which mirrors the logic of the provided Python solution. The code uses a sliding window approach with a hash map to track the count of fruits in the current window. Key differences include Java's explicit type declarations, the use of hashmap for the basket, and the syntax for handling default values. The logic ensures that at most 2 types of fruits are kept in the basket, and the maximum window length is calculated. To solve the problem, we use a sliding window approach. Starting with the first example, the input array is 1, 2, 1. We initialize the left pointer to 0, max_fruits to 0, and an empty dictionary called basket to store the count of fruits currently in our window. In the first iteration, at index 0, the current fruit is 1. We add 1 to the basket, which now becomes 1, 1. Since the basket contains only one type of fruit, which is less than or equal to 2, we calculate the maximum number of fruits collected so far as max 0, 0 to 0 plus 1, which equals 1. Moving to the second index, the fruit is 2. We add 2 to the basket, resulting in 1, 1, 2, 1. Again, the basket contains two types of fruits, so we calculate the maximum as max 1, 1 to 0 plus 1, which equals 2. At the third index, the fruit is 1 again. We increase its count in the basket to 1, 2, 2, 1. Since the basket still has only two types of fruits, we update the maximum to max 2, 2 to 0 plus 1, which equals 3. With no more fruits left to process, the final output for this example is 3. In the second example, the input array is 0, 1, 2, 2. We start by initializing left to 0, max underscore fruits to 0, and an empty basket. At index 0, the current fruit is 0. Adding it to the basket gives 0, 1. Since the basket contains only one type of fruit, we calculate the maximum as max 0, 0 to 0 plus 1, which equals 1. At index 1, the current fruit is 1. Adding it results in 0, 1, 1, 1. The basket now has two types of fruits, so we calculate the maximum as max 1, 1 to 0 plus 1, which equals 2. At index 2, the current fruit is 2. Adding it to the basket gives 0, 1, 1, 1, 2, 1. Since the basket now exceeds two types of fruits, we need to remove the fruit at the left pointer, which is 0. Removing it updates the basket to 1, 1, 2, 1, and increments left to 1. We then calculate the maximum as max 2, 2 to 1 plus 1, which equals 2. At index 3, the current fruit is 2 again. We increase the count of 2 in the basket, resulting in 1, 1, 2, 2. Since the basket contains two types of fruits, which is valid, we calculate the maximum as max 2, 3 to 1 plus 1, which equals 3. With no more fruits left to process, the final output for this example is 3. Now let's look at the third example, where the input array is 1, 2, 3, 2, 2. We initialize left to 0, max underscore fruits to 0, and an empty basket. At index 0, the current fruit is 1. Adding it to the basket gives 1, 1. The basket contains only one type of fruit, so we calculate the maximum as max 0, 0 to 0 plus 1, which equals 1. At index 1, the current fruit is 2. Adding it results in 1, 1, 2, 1. The basket now contains two types of fruits, so we calculate the maximum as max 1, 1 to 0 plus 1, which equals 2. At index 2, the current fruit is 3. Adding it to the basket gives 1, 1, 2, 1, 3, 1. Since the basket now exceeds two types of fruits, we remove the fruit at the left pointer, which is 1. Removing it updates the basket to 2, 1, 3, 1, and increments left to 1. We then calculate the maximum as max 2, 2 to 1 plus 1, which equals 2. At index 3, the current fruit is 2. We increase its count in the basket, resulting in 2, 2, 3, 1. The basket contains two types of fruits, so we calculate the maximum as max 2, 3 to 1 plus 1, which equals 3. At index 4, the current fruit is 2 again. We increment its count in the basket to 2, 3, 3, 1. Since the basket remains valid with two types of fruits, we calculate the maximum as max 3, 4 to 1 plus 1, which equals 4. With no more fruits to process, the final output for this example is 4. The time complexity of our solution is O(n), where n represents the number of elements in the input array, fruits. Let's break this down step by step. First, the outer for loop iterates through each element of the array exactly once, from index 0 to n1. This traversal contributes O(n) to the overall complexity. Now, within this loop, we have a while loop that activates when the basket dictionary contains more than two distinct fruit types. The key observation here is that the left pointer moves strictly forward, and each movement corresponds to one element being removed from the basket dictionary. Therefore, even though the while loop might execute multiple times, the total number of movements by the left pointer across the entire execution is at most n. This means the while loop contributes an additional O, n, in total. Lastly, operations inside the loops, such as accessing or modifying the dictionary and calculating the maximum, are all constant time operations, O1. These operations do not affect the overall asymptotic complexity, leaving us with a total time complexity of O(n). Adding the contributions from the for loop and the while loop, we have O(n) plus O(n), which simplifies to O(n) overall. Now, let's analyze the space complexity. The solution uses O(1) space because no additional data structures proportional to the size of the input are required. Here's a breakdown of the memory usage. First, the sliding window pointers, left and right, are simple integers that consume constant space, O(1). Next, the basket dictionary stores at most 2 key value pairs, since the problem limits the basket to hold no more than 2 types of fruits. This also requires constant space, O(1). Other variables, such as max_fruits and the current fruit, are scalar values that similarly consume O(1) space. Therefore, the total space complexity of the solution remains O(1). In summary, the solution's space complexity is O(1), as it does not require additional memory proportional to the size of the input. To put this into perspective, let's compare it to a brute force approach. A naive solution would involve generating all possible subarrays of the fruits array and checking whether each subarray contains at most 2 distinct fruit types. This approach would require O(n)² time to generate all subarrays, and for each subarray, it would take O(n) to check the distinct types of fruits. That results in a total time complexity of O(n)³. The space complexity, however, would still be O(1), as no additional data structures are used. The sliding window approach, in contrast, optimizes the time complexity to O(n) by dynamically adjusting the window size during a single traversal of the array. It also maintains the space complexity at O(1) by using a dictionary that holds only 2 entries at any given time. This makes the sliding window approach exponentially more efficient for large inputs. Now, let's analyze the algorithm in different scenarios. In the best case, the input array contains at most 2 distinct fruit types throughout. Here, the while loop never executes, and the solution completes in O(n) time. In the average case, the input array includes a mix of subarrays with more than 2 distinct fruit types, causing the window to shrink occasionally. However, even with such adjustments, the time complexity remains O(n). In the worst case, the input alternates between adding and removing fruit types, meaning the while loop executes frequently. Despite this, the left and right pointers together traverse the array at most once, and the total number of operations remains bounded by 2n. This ensures that the algorithm still runs in O(n). To mathematically confirm this, note that the movement of the left pointer in the while loop corresponds directly to removal operations from the basket dictionary. Since the left and right pointers each traverse the array only once, the total number of operations is proportional to n, guaranteeing an O(n) time complexity in all cases. When solving this problem, there are a few common mistakes to watch out for. First, not handling edge cases like empty arrays or arrays with fewer than 2 elements is a frequent oversight. These scenarios often cause runtime errors because no valid subarrays exist, and failing to account for them leads to incorrect results. Another common issue is misunderstanding the phrase "at most 2 distinct types." It's important to ensure that subarrays actually contain only 2 distinct fruit types and aren't overcounted by mistakenly allowing invalid subarrays with more than 2 types. Additionally, brute force implementations, while straightforward, are highly inefficient in this context. Generating all subarrays and checking their validity using nested loops results in a time complexity of O(n)³, which becomes impractical for larger inputs, such as arrays with tens of thousands of elements. Now, another frequent mistake involves incorrect sliding window updates. When you encounter more than 2 distinct fruit types, it's crucial to shrink the window properly. Failing to do so can lead to overly large windows, causing incorrect results, or overly small windows, resulting in redundant calculations. Another issue is not leveraging a hash map or frequency count to track fruit types. Simply using a list or set can cause premature removal of fruit types when shrinking the window, leading to errors. In terms of interview insights, mastering the sliding window pattern is key for this problem and others like it. A hash map allows you to efficiently track the frequency of fruit types, ensuring accurate window management. Also, discussing the trade-offs between brute force and optimized approaches showcases your optimization skills. Always explicitly mention edge cases, such as empty arrays or arrays with identical elements, to demonstrate thoroughness in your analysis. This problem is closely related to several others that also rely on the sliding window technique. For example, LeetCode 340, longest substring with at most k distinct characters, generalizes the concept to allow for any number of distinct characters instead of just 2. Similarly, LeetCode 159, longest substring with at most 2 distinct characters, is nearly identical to this problem but applies the logic to strings instead of fruit baskets. Another related problem is LeetCode 209, minimum size subarray sum, which also uses the sliding window technique but focuses on finding the smallest window that meets a specific condition. Finally, LeetCode 3, longest substring without repeating characters, explores a constraint on uniqueness, further demonstrating the versatility and importance of mastering sliding window problems in algorithmic problem solving. There are multiple approaches to solving this problem, each with its own trade-offs. The brute force approach, while simple to implement, has a time complexity of O(n) cubed and a space complexity of O(1). This makes it unsuitable for large inputs due to its inefficiency. On the other hand, the optimized sliding window approach drastically reduces the time complexity to O(n) and uses O(k) space, where k is the number of distinct fruit types. This approach is more efficient for handling large inputs but requires a deeper understanding of the sliding window technique and frequency tracking. An alternative is the two-pointer approach without extra space, which also achieves O(n) time complexity but reduces space complexity to O(1). However, managing type counts manually without a hash map can increase code complexity and the potential for errors. Choosing the right approach depends on the problem constraints and your familiarity with these trade-offs. Great job! To recap, we used the sliding window technique to solve the fruit into baskets problem efficiently. Remember, mastering patterns like this can give you an edge in interviews. Keep practicing and growing your problem-solving skills. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!